Right everyone, welcome to the part 2 of logic families, chapter number 6. So it is a TTL logic. Still now we discussed about RTL and DTL logic. Now we are moving to the TTL, transistor logic. Okay, this is a transistor logic is a saturated logic. We have two types of logic, saturated logic and a non-saturated logic, based on the transistor whether it is operating in saturation or non-saturation. Okay, so still RTL is a saturation logic and DTL is a saturated logic and TT is also saturated logic circuit. It is the most widely used because since 1970s, early 1970s, the speed and good fan in and good fan out are easily interface the digital literacy. In that particular year, this particular TTL is a very popular because of this particular features what I mentioned: speed, good fan in and good fan out. Already I mentioned fan in and fan out. We'll see at the end the characteristics of the TTL. Okay, so it is also easy to interface. After that, the unique feature of this particular circuit is multiple emitter transistor. So in the transistor, look at here, in the transistor we have a multiple emitters are present. Okay, so these multiple emitters are present, replaced by the diodes. So in the previous case, diodes are present in the input side. Here, in place of this totem, in place of this transistor, diodes are present. Now it is replaced by two emitter transistor. That is a major difference. Everything is remaining, everything is same. Next one, the basic total entire thing TTL is a basic family of is a NAND gate cell. So this particular working the truth table same as NAND gate. Okay. Now, however, at present, NOR gate and AND gate and so many configurations we have. The basic circuit of TTL is a NAND gate cell. Okay, it is represented here. NAND gate of this basic TTL. Now we'll see how exactly this particular circuit is working. It is obeys the NAND gate truth table or not, we'll see. Clear? Now, first, in the different cases we are going to discuss. The first case, both A and B are 1. Let me take both A and B are 1 and analyze the circuit working. This is the TTL logic. So, A is 1 and B is 1 in the first case. Truth table of NAND gate, A, B, and then output is C, for example. So both are 0, 0, 1, 1, 0, 1, 1. I am casing this case I am taking. Okay. What is the NAND logic you may expect? NAND is nothing but a output C is equal to AB whole bar. That is a NAND gate logic. So both are 1. 1 into 1, 1 bar, that will be 0. So you may expect 0. Let's see whether we will get the output is 0 or not in this case. So both A is 1, B is 1. So whenever A is 1, B is 1, this particular transistor emitter base junction, this is NPN transistor, emitter base junction is a reverse bias. Okay, emitter base junction is a reverse bias. Whenever emitter base junction is reverse bias, what about the transistor is a cutoff region? Okay, so emitter base junction is reverse bias. What about this VCC is connected to this collector base junction? Collector base junction is forward bias. Got my point? Emitter base junction is reverse bias. Collector base junction is a forward bias. Whenever it is a forward bias, the Q2, the particular Q1 is off state here. What about Q2 is on? That is saturation. Whenever Q2 on, what amount of VCC is present, that is flowing through, that is connected to R2 as well as this particular transistor and grounded. What is ground potential? 0. So this total entire things dropped across R2 and transistor. That means what about the output present here? 0. That means logic 0. Okay, clear? That is the first step. Next, second case, remaining case we will go into discuss. Let me take another color. Okay, right. So in the remaining cases, if it is both are 0, if 0 and 1 and 0 case, what will happen? We will see. Okay, Whenever both are 0 or any one input is 0, in these three cases together the same function will appear. See, whenever any input is high or both the inputs are low, what will happen? Transistor going to be okay. In this particular case, what will happen here? The Q1, the base emitter junction is forward bias. Base emitter junction is forward bias. Whenever base emitter junction is forward bias, Q1, that particular Q1 is on state. Whenever is Q1 is on state, what amount of VCC is present, that is connected, connected through the transistor whenever transistor is saturated. So now coming to here, the base as well as collector junction is reverse bias. Whenever it is reverse bias, there is no question of this particular transistor in the saturation region. That means that Q2 is off state now. All of you got my point. Q2 is off state because it is reverse bias. Whenever Q2 is off state, what amount of VCC is present? It is also connected through that, right? Yes or no? That means total entire drop across this particular resistor. That VCC is present here. It is a parallelly connected. So whenever VCC, this parallelly voltage present here, that voltage as a output logic 1. VCC may be 5 volt or 6 volt, whatever may be, VCC is present, that is a logic 1. Okay. So that means any input is 0 or both the inputs are 0, output will get 1. That's why it is a same as operation of NAND gate. Clear about TTL logic, working principle? Right. Now another thing, instead of, that is a basic circuit diagram we discussed about the TTL logic. In the TTL logic itself, we are added one more stage, that is a totem pole. This is a added one more stage. This particular stage is added practically. Okay, that stage you are call it as a totem pole output. Okay, everything is same still here. The working also. We are added one more stage, that is a totem pole stage. We will discuss that particular thing also. Okay, so why are added everything we will explain here. It is a modified version, added one more stage common to use. Why this extra output stage often taken is known as a totem pole stage. Because of the output components Q3, Q4 and D are stacked. Okay, so see here, R4, Q3, D and Q4, all these are stacked. So one of the top, another in the manner of totem pole. Okay, let us discuss the working. So the working, in the first case, both the inputs are 1. So in this particular notes, I make it directly working of this particular totem pole. I actually from the feedback from the students, the examination time is less. That's why this particular theory also not required, sir. Only directly the working in the short notes is required. That's why from this question onward, from this topic onwards, I make it the note simplifier and directly write the result. Okay, right. So now see here, both the inputs are high. Okay, both the inputs are high. So what will happen? Collector base emitter junction is reverse bias. Same working. Whenever it is reverse bias, it is forward bias. VCC is connected. Now Q2 is on, Q1 is off. Whenever Q2 is on, what amount of supply voltage VCC is present, that will be appears across here. That means it is grounded, like appears across here. What about N potential is decreases, that means Q3 is off state. Got my point? Now whenever it is this plus VCC is present here, more or less, that some potential is present here, that may be voltage, some potential is present here, that is drives the Q4, and the Q4 is on. Whenever Q4 is on, total entire thing is grounded through Q4. That means Q4 is saturated. The output logic you may expect it 0. Okay, clear? Now in the second case, either any one input is 0 or both the inputs are 0. In that particular case, what will happen here? So this particular transistor, whenever both are 0 or any one input is 0, the transistor Q1 is a on state. It is a forward bias base emitter junction. So whenever base emitter junction is forward bias, this is a base collector junction is reverse bias. Okay, so now transistor Q2, whenever it is a forward bias, it is reverse bias, Q1 is off. Coming to the Q1 output is connected to the Q2 base, that's why Q2 is also off. Clear up to now? This plus VCC, this plus, whenever it is off, this plus VCC appears across this R2 that is connected to Q3. Okay, that means that this particular voltage drives the Q3. Now Q3 is on. Whenever Q3 is on, what amount of plus VCC is connected through the saturation transistor to diode now it is forward bias, and through this particular point. Come back to here, some potential available. Now coming to the Q4, whenever it is off state, whenever Q2 is off state, what will happen? There is no question of Q4 potential. That means the Q4 potential is 0, the base value is 0 here. That means that Q4 is off state. Whenever this particular transistor is off state, what amount of plus VCC after the small drop, more or less plus VCC present at the output, that may be 1. Logic 1, because this VCC is present output. Even though small drops across the R4, Q3 and D, we can neglect the drops. We will consider logic 1 is a high. Okay, this is about the working of transistor totem pole output. Okay, now we are this is about the everything explanation. Now we'll see some two important points. Why are we using the D? If the purpose of D here, whenever D both the transistor not turn on at a time, so this diode is doing that. Okay, that is a provision of diode. Next, coming to the addition of pair of totem pole transistor to increases the operating speed and output current capacity of the circuit. That is the main advantage of totem pole. In the examination, you may expect it. What is the purpose of totem pole stays in the TTL logic? The importance is to increases the operating speed and output current capacity of the circuit. Let us see the characteristics of the TTL family. So the first characteristics is the greater speed than DTL. Yes, less noise immunity. It is around 0.4 volt. Average of propagation delay per gate is 9 nanoseconds, and the average power dissipation is 10 milliwatt. And fan out of 10 means one output can drive 10 other TTL inputs. Fan out is 10. One fan out means that one output can drive the 10 other TTL inputs. That is a fan out. So fan in is a 6. Okay, that is related to the input. This is about the TTL logic. Now I will give some important TTL family, TTL, some subfamilies of TTL. Okay, so these are also important. We'll see here 4 families, 4 sub-families we have important. We'll discuss. So first one is a 74L00. Here L is transfer low power consumption. That means that 74L00 is a low power consumption IC. It has an average power dissipation is 1 milliwatt per gate, but propagation delay is a 33 nanoseconds. The drawback here, propagation delay is a more. Next one, 74H00. Here this H is transfer I speed. Okay, it is a I speed. It is about 6 nanoseconds. Here 33 nanoseconds, but here I speed it is a 6 nanosecond. But here 1 milliwatt per gate, there is a power dissipation. But here drawback is the average power dissipation is 23 milliwatt per gate. Okay, that is the drawback. Now that's why you are moving to the next series 74S00. That means that this S represented the short key. That means short key diode is connected. It has the highest speed because it average power propagation delay is just 3 nanosecond per gate. However, the average power consumption is 23 milliwatt per gate. Okay, that is a power consumption is same as 74H00. That's why we have to overcome this power consumption. We are moving to the next IC, that is a 74L S00. That means that it is a S short key as well as L is also added. Okay, so L is a low power consumption because we have a drawback of low power consumption. This means that it is a recent variant of TTL family. TTL family, it is called as a low power. It is a low power short key TTL. It has an average propagation delay of 9.5 nanoseconds. Average power dissipation is 2 milliwatt. This somewhat better IC compared to all these subdivisions. Okay, this is about the TTL. Now we are moving to the next logic gate, that is the ECL. Okay, so here, okay, next important ECL, emitter coupled logic circuit. So it is a one of the available highest speed family device of IC family devices, IC family circuit, that is a ECL. Very important. You may expect the question from this area. So recently available logic circuit is primarily due to fact that transistors never operate fully saturated or fully cut off. That's why it is called, ECL is known as a non-saturated logic. Still now we discuss saturated logic. Now ECL speciality, why it is a high speed, because it is a non-saturated logic. That means that transistor cannot be operated in saturation, cannot be operated in cutoff. We can in between we are going to operate it. So this is a propagation delays are time varying from 0.9 nanoseconds to 2 nanoseconds. Okay, the time period. However, the power dissipation is increased since no one transistor is always in the active region. So somewhat power dissipation is increased, but the speed is high. So okay, so the another feature of ECL is the provides the output which always complement of each other. That means we have a two outputs, that is a Q1 and the last one Q4 and Q5. We will see the diagram there. We have a both outputs are dual, complementary each other. So that's why it is a operation based on differential amplifier. So it is also important point. The operation of based of ECL is a differential amplifier. We will discuss the working now. This family is particularly suited to monolithic fabrication. So fabrication is one of the IC fabrication integrated circuit chapter is there. We'll discuss different type of fabrication techniques. We are using the monolithic fabrication. This is also one of the bit you may expect, because logic levels are function of the resistors ratio. Okay, now we are moving to the working. This is a diagram for the ECL. So in this particular circuit, emitter is coupled. So that's why emitter coupled logic circuit. So this particular working I will explain. Before that, I will give you some important points. Here RVS, that is a voltage supply without affecting the temperature. This is a supply, is a constant current source which is driving the Q3. So now here the points here, the basic circuit shown in the figure, it is based on combined R and NOR circuit. The output you may expected, one of the output is R output, other output will be NOR output. This is a complementary each other. So next, and is operated from the VEE, just assumption minus 5.2 volt. For your understanding purpose, working purpose, I am taking this particular voltage. Built in the constant current source provided by the emitter. Okay, here the points you need to remember. Logic 1 is nothing but a minus 0.9 less negative. We are using positive logic only, right? So it is a less negative. Next, logic 0 minus 7.15. Whenever logic 0 minus 7.15, it is a more negative. That means that minus 0.95 is a less negative. 0.175 is a more negative. More negative is 0, less negative 1. That means that it is using the positive logic. For example, you are using the negative logic. The function would be AND and NOT gate. That may be question. Okay, in case of ECL circuit, we are using the negative logic. Which of the following function will be taking place? AND and NAND. If it is positive logic, R and NOR. Okay. Now throughout our explanation I am using the positive logic only, don't worry. Okay. Now one more important point here, the reference voltage minus 1.9 supplied to the Q3 from the built-in constant temperature temperature compensated reference voltage source or Vs. Okay, so let us discuss the first case. The first case, whenever the voltage, the first case here, when both the inputs are logic 0, that means logic 0 is nothing but a minus 1.75. Just now I mentioned the values minus 1.75, that is example assumption value. So in that particular case, what will happen? See here, both are 0, both are 0. Whenever both are 0, you know, Q3 is a more less negative. Q3 is a next negative compared to Q1 and Q2. That means that Q1 and Q2 are the off state. Both are off state. Now this constant current source, it drives the Q3 is on. Okay. So whenever Q3 is on, it is saturated from the base voltage supplied from the RVS. Got my point? So whenever base voltage supplied from the RVS, Q3 is on state. Whenever Q3 is on state, you know, this collector drops the voltage up to, let me take it is a minus 1 volt. So based on the total assumption, from that it is minus 1 volt is a drop, some voltage drop maybe. Okay, thus voltage drop across this particular R3. That means that this R3 drives the Q4. Yes or no? This drives the Q4. Now Q4 is on. This R3, this particular minus 1 volt drives the Q4. Q4 is on. Whenever Q4 is on, this particular voltage, this particular voltage of emitter is connected to R. Emitter is available, right? This is the R output. How it is? See, it is a minus 1 volt, that is a drop, as well as the base to emitter drop is a minus 0.7. in case of it is a silicon device. In case of germanium, it is a 0.3. It is 0.7. Now it is a minus 1.7 volt. You know, it is a minus 1.7 volt in this particular output. So it is a logic 0. Got my point? It is a more negative, right? More negative is nothing but a 0 volt. Coming to the Q5. Whenever Q1 is off, Q2 is off, both are off state. What about the drop across this particular case? This particular case only this base emitter drop only present. That means here 0 minus 0.7. Here the input here available here 0, and then here drop is 0.7. That will be minus 0.7. So minus 0.7 is nothing but a less negative. Less negative is nothing but a 1. Okay, got my point? That means that it is 0, you will get 1 here. That is a complement of input and output. In the same case, we are going to discuss about both the inputs are high, and then one of the input and one of the input is low, otherwise one of the input is high. What will happen? See, in the same case. So everyone is clear about the first case. And then second case, when either input A or B at logic 1, that is a minus 0.9. The output you may expect minus 0.9, logic 1. That is a less negative. So in that case, Q1 and Q2 both are on. Okay, whenever you are applying 1, otherwise any one of the input is high, Q1 is on. Let me take another color. Q1 is on and Q2 is also on. Both are on. Whenever these both are on, what about the Q3? Q3 is off state. Okay, whenever Q3 is off, both are on. They directly, whenever Q3 is off, what amount of this particular neutral is connected to the Q4? The particular Q4 is connected to the output logic 1, same as the notations I am given here. Okay, time constant I am not going to calculate it. In the same thing, What will happen for the Q5? Q5, this is on, right? It's drive the output of Q5. It is conducted on state. Whenever it is on state, the output available here 0. Okay, this is a more negative will get. So it is 0, it is 1. So same case criteria, the working of reverse case. So this is enough for the explanation, but you are attending the competitive exam. That's why final important conclusion I made from this video. ECL circuit is a very fastest circuit, but power consumption is more compared to remaining. But it is a fastest device at present available. Another thing, characteristics. So characteristics of ECL. The propagation delay time per gate is a 1 nanosecond. So meaning extremely fast speed, 1 nanosecond. And the power dissipation is 30 milliwatt. This was some drawback. And the fan out is a 50, fan in is a 5, and noise immunity is a 0.4 volt. These are about the characteristics. Okay. In the next part of the video, we are going to conclude this particular chapter. CMOS circuit and I2L IC family devices. Then we will end up this particular chapter. Thank you.